everybody! I hope everyone's having a wonderful day. So, last day I started talking about our first collision resolution called separate chaining. So remember, the idea was whenever I get a collision, I just use more memory. So the way I did this is I assume the table stored references to heads of linked lists. And then what I do is I simply treat each one of those heads as a place where I can perform an insertion. So the idea is that I just simply perform an insertion into a linked list where I index the list for which my hash function indexes into the table. So remember I told you how insertion, removal, that those are basically like inserting and removing into a linked list, just like what we see with dictionaries where the word about duplicates. So it's the same idea there. I talked about get, so the last thing I did was I showed you get. So recall, I'm given a key, and now I have to output the data for key k, so the value, and if k is not in the table, it gives me null. So remember, same idea. I index into the table using the hash keys value. Sorry, I get the hash functions output, so I'm going to hash into the table. I get a reference to a head of a linked list, and then I perform a while loop over that. I just simply go over each possible P here. Now, remember, the reason why this works is that I know that if I used my hash function, it had to have arrived me at that list by definition. Then on top of that, because of the correctness of my hash function, I know that it's going to simply go through, give me each one. It's going to traverse the linked list. Because we know how to traverse a linked list, we know that we're going to get through every single one of the elements. So if I get a match, I break out a loop. Otherwise, I might possibly get where it's null. If it's null, then I'm going to return null because I didn't find it. Otherwise, I return the data. And that's it. Very simple. So we're going to do a quick rundown of the analysis here. So I'm just going to count up all the operations of the lines this time. So line 1 is just going to take constant time, right? Because I'm just going to use my hash function. And at the same time, I'm just going to keep that a name. I'll call it C1. Line 3 is just getting the next reference. So inside this loop, if I evaluated this line, this takes constant time. However, I don't know how many times this is going to happen. Likewise, 4 and 5, these take constant time. So how long or how many times am I going to execute line 3? Well, it depends on line 2, right? So what is that going to be? Well, remember my picture last day where I had my linked lists? So what could possibly happen? Well, it's going to just simply be the length of that linked list. So that would be exactly how many it's going to have to go through, the length of the linked list. Possibly. So in the worst case. So how many times is this going to happen? It's equal to the length of the list. So the running time is just going to simply be the sum of all these things that I just mentioned, which is big O of length of the list. Now, in the worst case, you already get it, because in the worst case, this is very much the exact same scenario we had where I had my linked list implementation of a dictionary. The same idea is exactly the same one here. So it could be very possible with a very poor hash function that I just simply put all of my records into one of the lists. And so I have to traverse through the whole list, possibly all the way to the end. What is that? That's big O of n, where n is the number of records that are in the table. However, if I assume that my hash function is good, meaning it's going to try to spread across all of the table uniformly, and I assume my keys are going to be provided such that this is the possibility. In the average case, here's how I want you to imagine it. This is one way of going about it. Okay, remember, the number of, let's find a marker. The number of records that I have is n, and I've made the assumption that the size of the table is always going to be at least, so it's going to be the size of the table is greater or equal to the number of records. So the way you want to imagine this is like if I have a bunch of slots, and imagine my hash function was good in such a way that I give you some distribution keys to give it to the hash function such that they're uniformly distributed. So What would that mean here? That means that you would expect that each one of my keys, if I put in n keys in here, there's going to be how many collisions? You don't want to imagine it like I'm throwing balls into these boxes, such that they're not always going to expect to go one into each one of these boxes, right? Or at least some constant number as we're going to see. So the way I like to analogize is, imagine if I give you a bagel or your favorite thing you want to spread butter on, and you spread the butter. So the way you normally do this is you would imagine you're spreading the butter across the bagel surface. The same idea is sort of being applied here. So if it's uniformly distributed, that means I should expect there to be, there's going to be this case where it's just going to be some constant number of collisions that are going to happen, just like if I was spreading the butter across the bagel. Because it's uniformly distributed over a uniform spread of this table. And I promise this is not a butter commercial. So, so that being said, the average case is big O of 1. So I'm not going to get too much into the details, so I want to talk a little bit about this in more detail. So just to summarize things, so just give you a summary with separate chaining. I'm going to lay out all my operations. So I can perform get, put, and remove with separate chaining in place with my collision resolution. Okay, the worst possibilities in all of these are going to be linear. Just like our linked list implementation of a dictionary, that's what you will have in the worst case. However, you're going to have it where in the average case, and keep in mind when you design a good hash function, things like polynomial hash codes, they work pretty well in practice, so it will be something kind of like the average. I can't claim that it is that, but it's kind of like that. There are some that can have this behavior, but I'm not going to talk about those in this course. However, if I can just straight up expect that I'm only going to access a constant number of elements each time, this is going to end up being constant time because the hash function takes constant time to compute, and at the same time, this length of this list is going to be some constant. So if I assume that I have, say, only n, which is going to be no more than m, maybe at most one collision possible, probably on expectation. I'm going to go into more detail what I mean by this by describing and introducing you to the concept of a load factor. So I'm not going to go too much into the details of the average case analysis, but remember, just think intuitively like I have all my hash functions sufficiently able to, based on the keys provided to me by this average case analysis, that they're going to be uniformly spread across the table. Just like if I took out my knife, spread it across the table with a knife with butter. So load factor is going to be equal to n over capital M, where n is the number of keys. Let me just switch markers. Number of keys stored in the table. And capital M is the size of the table. So one of the design things I had to talk about with you was this idea of the table size. So what's an ideal size for the table? So over here, I made an assumption. So we assumed n is less than or equal to capital N. In separate chaining, we're going to use this concept of load factor to talk a little bit more about how you can use separate chaining and a lot more broader applications than you would for other collision resolutions. In separate chaining, it is possible for n to be greater than capital N. Do you see that? Can it be bigger? Well, remember, each one of my slots in the table is a reference to a linked list. I can technically I can keep putting in more and more records into this table. So, the time to traverse a list on average is big O of what? Now I already know it's something like a constant, but there's actually a more precise way of actually saying this. So I'm going to give you a better understanding of the average number of collisions that could possibly occur on this average case. So remember, I talked about the idea of the keys being uniformly distributed across the table. So this is an assumption I'm making. So I cannot make that assumption in my worst case analysis. I can't. Because the keys, I'm assuming, come from a distribution such that they're going to spread uniformly across the table. Well, what does that mean? Well, it's just on average. Because I've made the assumption that the hash function will spread them uniformly across. Okay? So if I make this kind of assumption, I want you to imagine, instead of putting butter on one piece of a bagel or a piece of bread, instead I want you to imagine I'm a baker. And as a baker, what I'm going to do is I'm going to make a layered cake. And so my job is to make a cake, and it has a bunch of layers to it. How many layers? Well, let's talk about that. So in my discussion of the butter on the bagel, I spread the keys uniformly across the table, which would be all my slots. Imagine this as one layer of the cake, and I put icing in between the layers of the cake. That's normally how you make a cake. You put layers in between the different stacks or layers of the cake, so I can get nice icing in between. It kind of comes out nice. Keeps it moist. So I put the layer across. Now, imagine I had the ability to put more more records into my table. Okay, well, under the same type of assumption where the table is going to uniformly distribute the keys across the table uniformly, what it's going to do is the next time I go through, what you should expect in your head is, instead of it just being where I have a bunch of slots and I throw balls into them, or this idea where I have the butter knife and it's going to spread them across my bagel, now you can imagine it's spreading them across the table like a layer of the cake. And as I introduce more elements, it's going to become proportional to what? So let's think about it. So if I have this here, there's M here. So there's M slots in here. So there's M of these. M slots, and I've uniformly distributed them across the table. So if I have less than M, I should expect that these are going to have no collisions really in it. So I'm being a little bit hand-wavy with this because I don't want to get into too many of the statistical possibilities here. But I find it very intuitive to explain it using this analogy. So I'm uniformly distributed, and then imagine I had another layer where I could put another item into each one of my slots. So remember, this is like my layer of a cake. So I should expect that these are going to get filled in uniformly if I have a really good hash function, and that's over a uniformly distributed set of keys. What happens here? So I uniformly distribute them again. Okay, I have another layer. Okay, how many layers are possible here? How many layers are possible? What is this growing proportionally to on average? Well, how many of these am I going to need? Well, this had M in it. Now imagine I gave you, say, 2 times M in terms of the number of records I put in. Well, how many layers is that? You're going to expect something roughly 2 layers of this cake. The answer is that it's going to grow proportionally to the load factor. So when you're looking at the collisions, it's actually going to be growing with respect to some constant plus the load factor. So this gives you some insight into how you can take advantage of the size of the table when you think about this. Okay, so if the number of hash table slots is at least proportional to the number of elements or records by some constant. So imagine I have just some constant. So imagine that n is, say, 3 times m. So what should I expect on average then? Okay, well, if it's 3m over m, what should load factor be approximately? If it's, I should expect it to be around there. 3, right? So if I keep the number of slots in the table, capital M, and n related by some constant factor, which you should think of intuitively like the expected number of collisions, this load factor. So as the load factor goes up, the expected number of collisions should go up as well. Just intuitively with this example with the layers of cake. Remember, I'm a baker. I layer my slots like this. So if it's by some constant, what can we say then? Then alpha is equal to n over m is big O 1, right? Is that interesting? So if I make sure that these are differing by at most some constant, so you get to pick the constant. So for example, if you want to look on average to avoiding a certain number of collisions, now remember, this is on expectation. It will not always happen. Remember, it's on average. So there's going to be cases where if you don't have under all these assumptions, it will not necessarily work perfectly to this. However, on average, you should expect something proportional to 1 plus alpha. So if I keep alpha being some constant, then you should expect all your operations for separate chaining to still remain constant on average. So all of these will remain average case complexities of big O of 1 without any relation to the load factor. So you have to pick that, and you can experimentally figure out what alpha might be ideal for you. So for example, if I tell you, okay, on average, you should expect this many collisions or something like that, this might be a good way of going about it in practice. So one remark, if the performance degrades, so if you just find that it's just not really doing what you want it to, and the load factor exceeds a constant value, what you're going to do is you're going to increase capital M and rehash all the records into a new larger table. However, what should you take notice of if I have to rebuild the entire table and the table's rather big? This is expensive, right? So rebuilding the table is expensive. So we should avoid this. So we want to avoid rebuilding the entire table every single time. So here's sort of the idea you have with separate chaining. Is I give you some expected way I want it to behave. What I could do is I could think of this load factor as kind of a nice measurement. So it's some constant factor times this many collisions or what you should expect, plus 1, or 1 is just some other constant. So you get to pick what you want alpha to be. So that would be basically what drives what the size of the table you should select initially should probably be. So if you know that you want so many expected number of collisions with some constant factor involved, what you do is you look at your data and say, hey, look, I'm going to have this many IDs possibly in my table, like my student IDs. I might like 10,000 or something. So if I want to avoid a certain number of collisions from occurring, I could maybe set the table to be maybe 5,000 or something like that, and I should have something that's like 2 times the constant in terms of the average number of collisions that can occur. However, if it gets way worse, you might need to literally take and build a brand new table. What I would recommend in practice is double the size of the table, probably would be more ideal. And then what you do is you just simply go through your entire table and you insert all of those into the new table using the hash function. And remember, now you have to rehash them all because, remember, M has changed. You can't just simply copy them over. You have to rehash all of them. Okay? So that's separate chaining. This is one that I would argue is probably one of the easiest ones to play around with. We're going to shift gears to talking about kind of a set of other ways of dealing with collisions. It's called open addressing. So you could view separate chaining like closed addressing. You'll see what I mean by open addressing in a moment. So what's one problem actually, before I get to this, one big problem with separate chaining? It's because I've sort of let the memory go loose, right? I could use a lot of memory when I'm doing separate chaining. So if space is expensive, so if you're doing something a little bit lower level and you don't have so much memory, you might not want to use separate chaining possibly. Separate chaining. Separate chaining may not be an ideal choice. An ideal choice. If we just want to use the capital M slots of table T, we must determine a consistent way to insert into T. What do I mean by this? Remember, if I just use the table itself and I just treat it like a lookup table directly, I'm going to run into collisions pretty fast. So I need some consistent way of dealing with things. Now, it just should go for as a taken Normally you would assume that n is going to be less than capital M. So the load factor is going to be expected to be something like less than 1. So it's going to be assumed that load factor is less than 1. Because obviously once I get it filled, it's going to be exactly equal to 1, and thus I'm going to have to rehash the entire table. So I'm just going to, usually in a lot of the things I'm going to play around with, I'll just assume it's going to be less than 1. However, it can be equal to 1. So I'm going to assume that an empty table has null references. It has null references. So I'm just going to assume that the whole table is just full of null references. This isn't quite like when we were talking about in separate chaining. In separate chaining, I had no references. Here, I literally mean you're going to have some type for your records, and you're going to put them into the table where I assume that all the slots are empty. If they're empty, they aren't referring to any particular object that is of that record, so meaning they're a null reference. So I'm just going to make that assumption about how I store records in the table. So here's going to be the idea. So here's the idea. So remember my analogy where I went to the store. No, I didn't go to the store. See, it's been eons. We went to the theater. I went to the theater and I found myself a spot to sit in. My friend was coming along and for some reason wanted to sit at my spot. So one way you can deal with that is by simply just letting your friend sit on top of you. I don't recommend doing that. I hear it's a little sketchy, unless you really are good friends. I'm just joking, of course. So that's one idea. Now remember, I'm not allowed to just allocate more memory. That's not what I'm going to do in open addressing. Instead, what I'm going to do is imagine I have room beside myself, where I can say, hey, look, if I'm occupying this seat, maybe the seat beside me might be available. So what my friend can do is they can hop, like a bunny rabbit, hop over to the next spot and take the next available seat. That is one of the main ideas here. So what I'm going to do is check. I'm going to check position P sub h of k. If null is there, it's technically worth noting that this might also be later on in our discussion delete label. So just keep that in mind. It's not going to come up until a bit. But something that resembles an empty slot. Then insert into T at this spot. At this spot. However, if T sub h of k has already a record, right? Already record there. So already there. You must put it somewhere else in the table. So this is the open part of open addressing. So in closed addressing, I just simply keep using the same address over and over again. Open addressing, I'm going to find somewhere else that's open in the table. Okay. So we use a probing sequence. We're going to use a probing sequence. Probing. Think like aliens probing you. Not literally. Just please don't imagine yourself getting probed. A probing sequence. So probing as in I inquire some more information so I can make or inquire another thing. So that's where probing is coming from. It is the questioning or inquiry to retrieve more information. So in our case, this probing sequence, we're going to use a probing sequence to tell, getting a little excited here, to tell us where the next position to check should be. Where should it go? So there's many different probing sequences that exist in the literature. I'm going to show you two of them. We will explore two probing sequences. We define these later. So the two are the following. So the first one is called linear probing. The second one is double hashing. So linear probing and double hashing. So those are the two. So in open addressing, I got to talk about what exactly is the collision resolution. Let's talk about what collision resolution is. What's the collision resolution? So in open addressing, the collision resolution is the following. So in open addressing, we probe to find the next available slot. The next available slot of T using a probing sequence. So this is going to be the main idea here. So we're going to have this probing sequence. I'll be giving you examples of probing sequences. The way you want to imagine this, and this is how I remember probing sequences. I like to, as I imagined when I did my theater analogy, I hopped. I like to think of it as a little hop and cute bunny rabbit. So I have a cute bunny rabbit that hops. And hops to each spot to find where it wants to put its little nest. So the bunny will find that appropriate spot by hopping there. That's at least what the bunny's going to try doing. So the probing sequence dictates where the bunny's going to hop. Oftentimes I'll refer to these following along the probing sequence as hopping or probing. So probing sounds a little bit colder. I like to think of hopping, like a cute little bunny rabbit. Just hopping, hopping, hopping. That's how I remember how probing sequences work. Just think of a bunny hopping. So just imagine that bunny hopping. Just a cute little bunny with the floppy ears. So let's talk about linear probing. So in linear probing, on a collision, check the next successive position. Of course, when I say this, I mean modulo m, until a spot to put the record is found. So I got to give you what the probing sequence looks like. So here's what the probing sequence is. Remember, just think of the cute bunny hopping. Probing sequence. So first you're going to check h of k. So if you find an h of k, so I look in this position of the table, if I find an empty spot, I put it there. Now if there's something already occupying that spot, what I'm going to do is I'm just going to then proceed to check h of k plus 1 mod k. Now, if there's a spot available, I put it here. I hop to this position, I put it in. Now, if it isn't, I'm going to perform another hop. I'm going to check h of k plus 2 mod m, and so on, so on. So you would have h of k plus 3 mod m, and so on. You do this until you've checked every entry of the table. Now, it's worth noting that in practice, you would typically select the table size in linear probing to be a prime number. Prime numbers typically work really well as table sizes. That's usually a good practical way of doing things. There's some of these, as we're going to see, that require that the table size is prime, at least for a guarantee of it working properly. This one doesn't require that the table size is prime, so just keep that in mind. So this is the probing sequence. So remember, I'm the cute bunny, I do my hops. I hop, 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 until I find the available spot. Okay. So let's talk about how we would do this. So let's look at get. I find get tends to be pretty natural to look at. So let's look at get. So what should get do? Well, I gave you the process for which you're supposed to check each position until you find one, right? So let's just do that. So what's get going to do? It's going to apply the probe sequence. Apply the probe sequence. Follow until you find the key. You find the key. And then you just return null. So you simply return null if you encounter null. So remember, this is going to go through the probing sequence. I'm going to assume that when I insert things into the table or insert my records, each time I go to the appropriate spot that's first available to me and I put it there. Now, if I encounter a null, that means that it can't be anywhere else in the table. So that's a very big observation here. So if I find out that it's null when I do my hop, like little cute bunny rabbit, that means I didn't find it. So, or it checks all of T. That means I keep doing my linear probing all the way through. I keep doing this until I've hopped enough times that I've looked at the entire table. And once I've done that, I know I'm done. It's not there. Now, just as a note, as I mentioned before, I said, okay, well, if it's null, you should treat null and a label like delete, which we'll talk about later, as some sort of placeholder for an empty slot. This delete is going to play an important role when we talk about removals, but I'm not going to put that in quite yet here, but I made a note in the notes where you'd realize where exactly this might need to go. So let me write down get. Let's get the algorithm out. Let's go get. So get is going to be given as input a key k, as output. So it's output. What's it going to get? Data for key k, or null if k is not in T, not in the table. So that's my input output. Here we go. So I'm going to assign a variable called pause. I'm going to assign it to be the value that I get out of the hash function. So h of k. I'm going to have a counter variable called c. It's going to be used for my offsets. Actually, not in particular, it's going to be used, sorry, I should be a bit more precise. The c is going to be the number of hops I perform. So I want to make sure that I keep track of how many hops I do. Remember, that cute bunny just can't be hopping forever, right? The bunny's going to run out of energy eventually. It is not the Energizer Bunny. So what I'm going to do is I'm just checking if t sub pos is not equal to null, and t sub pos dot get key. So I'm going to get the key of the record in that position, and if it's not equal to k, what are we going to do if that's the case? So these two conditions are encoding ideas I have up here. So remember, if it becomes equal to this, that means I didn't find it. It means it's unsuccessful search. If I find where it's actually equal, that means, like in our other example of get, that means I found it, right? So what am I going to do? So remember, if I find this, I don't need to apply the next one of my probes in my probing sequence. I don't have to do another hop. However, I might have to. That's the purpose of this while loop. So pos is going to now be assigned pos plus 1 mod m, and c is going to be assigned c plus 1. So I'm going to increment c. So remember, this is just me going to the next probe in my probing sequence, and I'm going to increment my counter, telling me how many hops I performed or how many probes I performed. It's quite infamous. You see, you got to watch out. You don't want to be like one of the aliens in a sci-fi movie. Don't get too aggressive about probing. People don't like that. So if now we're going to just have an if statement in here, just checking to make sure that we haven't checked all the elements. I'm going to check if c is equal to m. So you know that it's going to be c is equal to m if I look at the entire table because of what? Because of what? It starts off at 0, it becomes 1 after I perform 1 hop, right? Then it performs 2 hops, then 3 hops, then 4 hops. However, you should notice that if I do this again, that means if I get up to, say, m minus 1 hops, I might possibly have to come wrap around. However, I know for certain if c is equal to m, I've looked at every single one of the entries in my table. All the slots. Then what happens? Then I should return what? Return null. I return null. I return null. And that ends the while loop. I got a little bit more left to go. Just 2 lines. So let me just write down the last 2 lines up here. I'll draw a dramatic arrow, but I'm going to come a segment in between these 2. So the last part of this, so stop there. So this is outside the while loop. If T sub plus is equal to null, meaning one of those two conditions, the first one got invalidated, then return null. We didn't find it. Otherwise, it isn't null, right? It means I found the key and I broke out of this while loop when the key equals my desired k. Otherwise, we're just going to return. We return T sub pos, so I get the record, and then I get its data. And that's it. That's pretty simple, right? We're going to get for the separate chaining, except instead we have these hops that are happening. So I have my probing sequence. So let's talk about time complexity here. So let's consider the worst case time complexity here. So we should look at this. Okay, so I have this line here. Let me pull out a different colored marker here. Let's go with pink. Pink is exciting. How long does this take? It takes constant time, right? Because that is the computation of our hash function. This line, that takes constant time, right? It's just some assignment. Okay, all of these inside here, each one of those operations takes constant time. All of these will take constant time. All those take constant time. Now, if you're counting the lines, what you would do is you'd select this line to count, if you wanted to do it that way. This way, I'm just counting them all up. So each one of these takes constant time. These two up here, how long do these take? Take constant time. So everything is entirely driven by this while loop. So this is going to be, so this altogether is some constant times the number of iterations of this. So some constant times some number of iterations. So this is me being a little informal here. What you would normally do is I would tell you, okay, there's some constant times some number of iterations for the while loop. So everything's determined by the number of iterations of that loop. So what would that be? So it's very real and possible, believe it or not, for my probing sequence to have to go through each and every single one of the elements in hash table, performing all the hops. So in the worst case, the while loop performs at most n iterations. So the worst case time complexity, is big O of n. So you would end up with a bunch of constants sitting outside the loop. There's another constant inside here, and then you're going to have some constant times the number of iterations. It's in the worst case, it's possible that you might have at most n iterations, so it's some constant plus some other constant times n, which is big O of n. See, it's pretty straightforward. So, anyways, we're going to stop right here, and when we come back, we'll do an example of using linear probing, just so you can actually see this thing in action. So, that being said, thank you very much, and have yourself a beautiful day.